Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello and welcome back. I hope you're well. Today we're going to talk about the group of organic compounds called halogenoalkanes. So we're going to talk about what is a halogenoalkane. We'll mention their general formula, talk a bit about their bond polarity and physical properties, and a bit about their reactivity as well. So what is a halogenoalkane? Well, as the name suggests, these are a group of compounds that are alkanes where one or more hydrogen atoms has been substituted by halogen atoms. These compounds are sometimes referred to as haloalkanes as well. You may hear or use that expression instead. And just in case you're not aware of all the halogens, we're talking about fluorine, chlorine, bromine, and iodine when we're talking about halogens in this context. When it comes to naming of halogenoalkane compounds, I did talk about how we do that in a previous episode about how to name organic compounds, and I'll put a link in the episode description if you want to have a listen to that. So a little bit about bond polarity. Each halogenoalkane molecule has a bond between a carbon and a halogen atom. In each case, the halogen atom will have a higher electronegativity than the carbon atom. So there will be a difference in electronegativity between the carbon and the halogen atom. The bond is therefore polar, with the halogen end being delta minus and the carbon atom being delta plus. How polar is it? Well, that depends on which halogen atom the carbon is attached to. Fluorine has the highest electronegativity of all elements, and therefore the carbon to fluorine bond is quite polar. Chlorine is less electronegative, and therefore the carbon to chlorine bond is polar, but not as polar as the carbon to fluorine bond. The carbon to bromine and carbon to iodine bonds are respectively less polar again because the bromine and iodine have electronegativities much closer to that of carbon. In each case, the polarity of the carbon to halogen bond doesn't make the halogen soluble in water. The intermolecular bonding in halogenoalkanes is a combination of van der Waals forces and dipole-dipole interactions between the polar bonds. The boiling points increase as the length of the alkane chain of the molecule increases, and also increase as the halogen goes down the group 7. In both cases, this is down to the increase in van der Waals forces. You'll remember when we talked about alkanes in a previous episode, we mentioned that the larger the molecule, the greater the interaction, the van der Waals interaction between individual molecules, and therefore the greater attraction between one molecule and another. That's the same situation that's happening with halogenoalkanes. A greater interaction because of greater chain length means that there is greater intermolecular forces to break down, and therefore the boiling point is higher. Additionally, as we go down group 7, from fluorine to chlorine to bromine to iodine, the atom size and the number of electrons in it is increasing. And therefore, the van der Waals forces between individual molecules will be increasing too. And therefore, that is why boiling points increase as the halogen goes down the group 2. When it comes to an halogenoalkane's reactivity, the reaction usually takes place at the carbon to halogen bond. That bond is usually broken during most reactions that the molecule will be involved in. So if we want to compare the reactivity of halogenoalkanes based on which halogen is in the molecule, there are two considerations we need to think about. One is the bond polarity of the carbon to halogen bond, and the other is the bond strength or the bond enthalpy of that bond. Let's think about the bond polarity first. We already mentioned that as we go down the group, the carbon to halogen bond polarity decreases considerably. Carbon to fluorine being quite a polar bond and carbon to iodine being not very polar at all. The more polar bond means that there is a bigger delta positive charge on the carbon and a bigger delta negative charge on the halogen atom, and that would make that bond, that region of the molecule, more attractive to nucleophiles. That is, compounds that are attracted to positive charge that want to react at the delta positive carbon. So The bond polarity on its own would suggest that fluoroalkanes would be more reactive than the other halogenoalkanes. But we said there was another consideration too, and that was bond enthalpy. Well, the bond enthalpy of the carbon to fluorine bond is very much higher than for the other carbon to halogen bonds. In fact, it's even stronger than the carbon to hydrogen bond. And in a previous episode, we've already mentioned that's a very strong bond in its own right. So as we go down the group, we find decreasing bond enthalpy in the carbon to halogen bond. So carbon to fluorine is a very strong bond. Carbon to chlorine is the next strongest of the four, then carbon to bromine and carbon to iodine. And carbon to iodine has the lowest bond enthalpy of the four that we're considering. So this would suggest that iodoalkanes would be the most reactive of the halogenoalkanes. And in fact, experimentally, we would find that's the case. We would find that bond enthalpy is the overriding factor more than bond polarity. It is the iodoalkanes that are more reactive than the bromoalkanes, and then the chloroalkanes, and least so the fluoroalkanes. In fact, fluoroalkanes are so unreactive that we famously use one of them, PTFE, as a non-stick coating on saucepans and use it in other applications where it needs to be very stable as well. We'll talk more about the types of reactions that halogenoalkanes undergo in the forthcoming episodes. If you have any questions on this topic, you can come and ask them in the podcast's Patreon community. So come to patreon.com/chemistrymadesimple and ask that question. You can also find me on Instagram at chemistrymadesimple and contact me there if you wish to. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistrymadesimple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself and goodbye.